Right now, above your head, an object that left its home before humanity existed is crossing the inner solar system. We call it 3I, Atlas, the third confirmed interstellar visitor ever detected. In our last investigation, we looked inside the molecules, the chemistry, the galactic recipe for life. But today, we ask a different question. Where did it come from? July 1st, 2025. The Atlas survey in Chile flags an unusual object. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a network designed to catch objects that could threaten Earth. But this isn't a threat. Within hours, the orbit calculations come back, and they're extraordinary. The orbit isn't an ellipse like every comet born in our solar system. It's a hyperbola, an escape trajectory, a one-way path through the cosmos. The I in its designation stands for interstellar, third confirmed visitor in human history. And that means one thing. This traveler doesn't belong here. It never has. It never will. But astronomers in Spain at the University of A Coruña decided not just to observe it, they wanted to rewind its journey, to trace its road through the stars backward through time. They turned to Gaia, the European Space Agency's revolutionary star mapping mission. Gaia has cataloged 1.8 billion stars with micro-arcsecond precision. It doesn't just measure where stars are now. It measures how they're moving, their velocities, through space down to millimeters per second. With that data, you can reconstruct where every star was in the past. You can rewind the galaxy itself. The team fed the comet's trajectory into the Gaia star map and ran the simulation backward, star by star, gravitational pull by gravitational pull. They watched its path unwind through space, not for years, not for centuries, for 10 million years. Let that sink in. 10 million years of galactic motion, reconstructed and reversed. They watched the comet's path thread backward through the Orion Spur, the glowing lane between two of the Milky Way's spiral arms, where our sun currently resides. They watched it drift past stars that have since burned out or exploded, through regions of space that were once stellar nurseries and are now silent voids. And after 10 million years of rewind, the simulation converged on a region near the galaxy's inner edge, a scarred neighborhood marked by old supernova remnants and ancient metal-poor stars. Could this be where it was born? Every comet begins as part of a larger story, the birth and death of stars. Our own solar system formed 4.6 billion years ago from a collapsing molecular cloud. As the sun ignited at the center, the leftover material formed planets, asteroids, and comets. The icy bodies were pushed to the outer edges, the Kuiper Belt and Oort cloud, where they've orbited quietly ever since. But not all systems are so stable. Not all stars live peaceful lives. When a star like our sun reaches old age billions of years from now, it will swell into a red giant. Its outer layers will expand beyond the orbit of Mars, boiling away the inner planets. The outer planets and their moons will be pushed outward by the star's dying breath. And the comets, many will be ejected, entirely flung into interstellar space by gravitational chaos. For more massive stars, the end is even more violent. They explode as supernovae, titanic blasts that tear apart everything bound to them. Planets, moons, asteroids, comets all become shrapnel scattered across light years. The Gaia reconstruction places the comet's origin near a cluster of ancient, metal-poor stars. These are old stars, second or third generation after the Big Bang. Many have already exhausted their fuel. Some have gone supernova. Others have collapsed into white dwarfs, their planetary systems stripped and scattered. Some astronomers now believe this visitor could be planetary debris from a system that died long ago. Its chemistry supports this. The high carbon dioxide content, roughly 3 times higher than solar system comets, fits the profile of a body that formed far from its parent star in the cold outer reaches where CO2 condenses before water. But there's another detail. The comet's surface shows signs of prolonged exposure to cosmic radiation, far more than our comets, which spend most of their time sheltered in the Oort cloud. This object has been wandering in the open for a very long time. A fragment of ice and dust, torn from its homeworld, hurled outward by a dying sun, and set adrift into the galactic dark, alone, for 10 million years. Once ejected, the comet became part of the galaxy's quiet migration, the slow river of debris drifting between stars. Interstellar space isn't empty. It's filled with gas, dust, magnetic fields, and radiation. The comet crossed regions of ionized hydrogen, glowing clouds lit by nearby stars. It drifted through molecular clouds where new stars were forming. It passed through the local bubble, a vast cavity blown open by ancient supernovae, now filled with thin, hot gas. And through it all, radiation carved its surface. Cosmic rays, high-energy particles accelerated by supernovae and black holes, bombarded the ice. Each impact broke chemical bonds, creating new compounds. Ultraviolet light from distant stars baked the outer layers, driving off the most volatile molecules and leaving a darker, carbon-rich crust. Its outer ices sublimated and refroze thousands of times as it passed near distant stars. Each heating and cooling cycle left marks layers of altered chemistry, like tree rings recording environmental history. By the time it entered our system, the comet was a time capsule. A survivor of countless gravitational encounters with stars, it passed but never orbited. A relic carrying the chemical handwriting of a dead system and the scars of the interstellar medium. Think about what it witnessed. Stars igniting and dying, planets forming around young suns, supernovae lighting up the galaxy, all while drifting silently through the dark, too small to be noticed, too cold to emit light. For 10 million years, it was invisible, a ghost moving through the cosmos, until it wandered into our light. In late October 2025, it reaches perihelion, closest approach to the Sun, at about 1.4 astronomical units. That's just beyond Earth's orbit. Then in mid-December, it drifts past Earth at a safe 270 million kilometers. No threat, no danger. Just close enough to study. For a few weeks, every major telescope on Earth and in space turns toward it. JWST points its infrared instruments at the comet's coma, the cloud of gas and dust boiling off as sunlight warms the ancient ice. NIRSPEC and MIRI capture spectral lines with exquisite precision, revealing molecules down to parts per million. ALMA in Chile locks onto radio wavelengths, measuring isotope ratios, deuterium to hydrogen, carbon-13 to carbon-12. These ratios are fingerprints. They reveal the temperature of the cloud where the comet's ice first froze billions of years ago. The Very Large Telescope in Chile captures high-resolution images and polarization data, studying the dust grains mixed with the ice. Their composition tells us about the minerals present in the original protoplanetary disk. Each wavelength tells a piece of the journey. The carbon signature hints at a cold origin formation far from the parent star where carbon dioxide ice is stable. The isotopic ratios whisper the temperature of the molecular cloud where the system first collapsed, likely colder than the cloud that formed our Sunday. The erosion lines carved into its surface reveal how long it wandered between stars, millions of years exposed to cosmic radiation without the protection of a parent star's magnetic field. The organic molecules frozen in the ice, methanol, formaldehyde, hydrogen cyanide, tell us about chemistry that happened in another system's protoplanetary disk under different conditions than ours. We are, in a sense, watching a message return to light. a traveler from a lost sun, gliding through our neighborhood just long enough to be recognized, just long enough to tell its story before disappearing forever into the cosmic dark. This is the closest we'll ever come to visiting another star system with our current technology. We can't send probes there, but sometimes, rarely, pieces of those systems come to us. 10 million years ago, a star died. Maybe it was a red giant that puffed off its outer layers, leaving a white dwarf ember behind. Maybe it was a supernova that lit up an entire spiral arm for weeks before fading to a neutron star or black hole. Either way, its planetary system was destroyed, torn apart, scattered. Its fragments were cast into the dark. Most fell silent, invisible, wandering the space between stars forever. But one of them, small, cold, and patient, has found its way here. From its trajectory, we trace the orbits of vanished stars. We see where the galaxy was 10 million years ago, before our sun completed half an orbit around the galactic center. From its chemistry, we read the fingerprints of forgotten worlds. We learn what molecules were common in another system's disk, what temperatures existed, what kind of star shone at the center. From its silence, we learn how galaxies recycle themselves, how death in one system becomes the raw material for life in another. Because here's the deeper truth. Everything in our solar system, including the atoms in your body, came from dead stars. The iron in your blood was forged in a supernova. The carbon in your DNA was created in the cores of dying red giants. The water you drink may have originally frozen in another star's debris field before drifting here and being captured by our young Sunday. We are made of stardust. That's not poetry. That's nuclear physics. And this comet is proof that the process is still happening, that the galaxy is still mixing. That material crosses between systems, carrying chemistry, carrying history, carrying the seeds of what might become life elsewhere. Perhaps that's the meaning of the visitor. Not a warning, not a mystery, but a reminder that nothing in the universe truly stands still. Everything drifts, everything transforms, everything is connected across distances we can barely imagine. Stars die, their children scatter, and sometimes across the endless dark, something finds its way back into the light. Long enough for us to see it, long enough for us to read its story, long enough to know that we're part of something much larger than ourselves. The spectra are still coming in. The trajectory refinements continue. Over the coming months, astronomers will publish papers analyzing every detailed composition, isotopes, dust, grain, mineralogy, trajectory uncertainties, formation scenarios. We'll learn more about where it came from, which region of the galaxy, what kind of star, how long ago the system died. But we already know the most important thing. For 10 million years, this fragment of a dead world traveled alone. And for a few brief weeks in late 2025, it passed through our light, close enough to be studied, close enough to tell us that the road through the stars is longer and stranger than we ever imagined. Close enough to remind us that the galaxy is a place of endless recycling, that nothing is ever truly lost, that the atoms that made one world will someday make another. And maybe, just maybe, that the ingredients for life travel farther and more often than we ever suspected. Watch the data with us, because every spectrum, every measurement, every calculation is another page in the story of how matter moves through the cosmos. This isn't just one comet's journey. It's the story of how galaxies live.